Hi guys, in this session let us consider core laws of transformer. Concepts also I'm going to concise, short and sweet. And also problems I considered all together new problems except one problem, because that one problem, old gate problem, is connecting to the concept, so I considered that. Okay, remaining problems are not literally from our workbook, also not from GATE or not from ESE. Very beautiful problems, you would love it. And second thing is, whoever joined with our YouTube subscription recently, means we are maintaining the videos as per the sequence only compared to last year. Okay, so you are supposed to watch last year videos also, this year videos also, because last year we went in different way, but this year we are going in a different way. Okay, anyway, if I think of transformer till now in a short and sweet, I'm not going to discuss much. Okay, so till now whatever the transformer we considered, okay, at no load conditions, load is not connected, and if I connect one voltage source here, no load current is not considered, because no load current of transformer is least compared to all other machines. That's a different story, forget about it. But now if you see, this is V1, it has to take no load current, and depending upon this current only flux will be generated, and because of that flux only induced voltage E2 will come here, induced voltage E1 will come here. Okay, and the moment this is magnetic field, in ideal conditions of iron, means losses will not be there here. When losses are not there, or in order to set up the magnetic field, we need not supply any power, or we need not lose any power, but current has to flow, voltage has to be there, meaning that with respect to voltage, current should lag behind 90 degrees, because it's inductor only. Current should lag behind voltage by 90 degrees, like network theory inductor. Okay, such that means active power taken or actual power taken from the source is going to be 0, meaning that in this condition it should be, if it is V1, I0 would be here, it is going to be 90 degrees, such that voltage, current, cos of the angle, cos 90 is going to be 0. So my source need not supply any active power, to be precise. Okay, now let us consider the practical case of the iron. Okay, practical case of the iron, you are going to have core loss. Okay, that core loss can be divided into hysteresis loss, eddy current loss. What is hysteresis, what is eddy current, forget about it. These can be divided into two. Okay, the moment losses are included now in iron core, then means in order to compensate that, only source availability is this, so this is supposed to supply power. Okay, meaning that now current, if you consider loss component, okay, or losses of the iron, my current should lag behind voltage by less than 90 degrees. Then only it will be able to supply power, no? V1 I0 cos theta naught is less than 90, so my source is able to supply power. Get my point, right? Now forget about it, more than that nothing is required. Now let us consider eddy current loss. Eddy current loss directly proportional voltage square as operating engineer only. As operating engineer, V equal to root 2 pi f B max ACN. As operating engineer, number of turns are constant, because the design engineer can change number of turns, operating engineer cannot, because the machine is manufactured by that time. Area of cross section of the core. Okay, then root 2 pi. As operating engineer constant, as operating engineer, V is directly proportional to B max F. So voltage square directly proportional to B max square F square. Okay, now let us think of as design engineer. I'm not going to, with the reasons and all, directly I'm giving how to concise the concepts, that's it. Okay, now eddy current losses as designer directly proportional to volume of iron, because immediately after this we are going to take a beautiful problem, you would understand. And again, eddy current loss is directly proportional to thickness of lamination square. These two as design engineer. Okay, volume of iron or thickness of laminations can be changed only by design engineer. This is going to be the case. Now let us think of hysteresis. Okay, so hysteresis losses directly proportional to B max to the power of X into F. This X is called as Steinmetz constant. Okay, means in practice roughly it should be around 1.6. Okay, but in your exam they don't give 1.6, they prefer 2. because if it is too easily can be solved, and they don't want to check how means your capability of using of that virtual calculator. Means if you think of old gate or ESE, every time they have given x Steinmetz constant as 2 only. Okay, because calculation will become easy. Now this is as operating engineer. Okay, meaning that hysteresis loss directly proportional to Bmax. Bmax is directly proportional to V by F. So V by F to the power of x into F. Okay, forget about it. Main thing is here. Now next thing is as design engineer. As design engineer, hysteresis loss is directly proportional to volume of iron. Volume of iron. Meaning that as a design engineer, hysteresis loss also depends upon volume of iron. Eddy current loss also depend upon volume of iron. But eddy current losses depends upon thickness of laminations, and hysteresis loss will not depend upon thickness of laminations. Okay, these are enough to solve the problem. See, such a beautiful problem. The iron loss in a transformer is 240 watt, out of which 48 watt is eddy current. Already I said in our sessions, right? Means eddy current losses should be less and hysteresis losses will be more. Okay, now if amount of iron in magnetic circuit were doubled by doubling the cross section area of the core, what would be iron loss for same impressed voltage and frequency? Consider Steinmetz constant as 2. First of all, we have to focus on whether this is design engineer problem or operating engineer problem. They are saying clearly area of cross section of the core is getting increased. When area of cross section of the core is increased, obviously it should be design problem. Okay, now see here, let us think of total core loss here is 240 watt, and here eddy current loss is 48 watt, and hysteresis loss 192. Done in the first case. And now in the second case, what they are trying to do were double the magnetic circuit. If amount of iron in magnetic circuit were doubled by doubling the cross section of the core. Okay, cross section of the core is doubled, length of the limb is maintained same. Okay, such that how these losses vary. Okay, try to focus here, it's a very good thing. Now see here, if I think of any losses directly proportional to volume of iron. Okay, now let us think of eddy current loss. Eddy current loss directly proportional to volume of iron. Okay, now volume of iron is increased by 2 times. So eddy current loss should be increased by 2 times. Okay, and also one more thing is there. Okay, you should not say directly. Okay, now next thing is eddy current loss is directly proportional to Bmax square F square. Why I am considering this? Because see, though they have varied design, and at the same time operation engineer part also is decided by them only, because who will maintain voltage and frequency? Okay, supply voltage and supply frequency for a manufactured machine should be supplied by operating engineer. Okay, for example, one transformer is there, means that is designed for 50 Hz, but you have 75 Hz. If you supply 75 Hz, you are an operating engineer, because machine is already manufactured. They are saying same voltage, same frequency, meaning that whenever you have design part, automatically operating engineer part also will come, because means the design variations they will specify, and with this design variations, if I use at this particular voltage or this particular frequency, what will happen is the question. Okay, in that conditions operating engineer also will come. Now let us think of complete equation. Okay, V equal to root 2 pi f Bmax AC n. Okay, now root 2 pi anyway constant, and frequency they said that same voltage same frequency they have given, so frequency is same, voltage is same. Number of turns they did not say anything, so we have to consider constant, and area of cross section of the core is doubled, meaning that Bmax will be reduced by 2, because remaining everything is going to be constant. No, so Bmax is going to be half now. Now coming to here. Now in this, eddy current losses directly proportional to Bmax square F square. In this, okay, in this Bmax is reduced to half. Bmax is reduced to half, and frequency is going to be same. So from operating engineer point of view, eddy current losses should have been reduced by 4 times. Now let us combine this and this. from design point of view, it should be increased by 2 times. My operating engineer point of view, it should be reduced by 4 times. Altogether combinedly, it should be reduced by increment by 2 times, decrement by 4 times. So net should be decreased by 2 times. Okay, so if you think of total eddy current loss now, okay, so total eddy current loss nu is going to be half of 48 is going to be 24 watt. Keep it aside. Okay, you will not find this question anywhere, frankly. Now let us think of what do you say, hysteresis loss. Okay, hysteresis loss as a design engineer. Hysteresis loss as a design engineer directly proportional to volume of iron. Now volume of iron is increased by 2 times. Volume of iron is increased by 2 times. So hysteresis loss should be increased by 2 times as design. As design. Now let us think of operating engineer, because same voltage, same frequency, some kind of stuff they have given. Okay, so hysteresis loss directly proportional to B max to the power of x square 2 into f. Now B max is reduced by black. Okay, B max is reduced by 2 times, meaning that B max square is going to be reduced by 4 times. Okay, and frequency is anyway same frequency, so hysteresis losses should be reduced by 4 times. Okay, why it came? If you would have taken 1.6, difference will come between this and this, but now difference may not come. Now hysteresis losses means for the given voltage, frequency and all, hysteresis losses should have been reduced by 4 here, hysteresis losses should have been increased by 2 times here. So net hysteresis loss means from here it should be increased by 2 times, from here it should be reduced by 2 times. Now net should be reduced by 2 times. So from here hysteresis loss dash equal to 192 by 2. Okay, is going to be, that's it, plus 24. So net core loss in the second case is going to be, this is half, or 240 by half, that is going to be 120 watts. Okay, this came because I considered Schmitt's constant as 2. Otherwise, if I have considered 1.6, okay, so B max to the power of 1.6 into f, if I consider frequency is going to be same, so B max to the power of 1.6, in the sense difference will come between hysteresis and eddy current percentage variations. Now let us take this question. This is already all of you know. Okay, but anyway, let me deal once. A single phase 10 kV 50 Hz transformer with 1 kV primary winding draws 0.5 amperes, 55 watt and rated voltage, frequency unknown. All linear dimensions are increased by root 2 times. All linear dimensions are increased by root 2 times. You know the answer, I know. Okay, just let me deal the way how we dealt the previous question. Okay, is this design engineer question or operating engineer question? If you want to read the question, you can pause the video and you can go ahead. Okay, so this is going to be design engineer question, because volume is increased by root 2 times. Okay, means each linear dimensions are increased by root 2 times. Root 2, length is root 2, so 2 root 2. Now if you think of hysteresis loss directly proportional to volume of iron, and as an operating engineer, because that also should be taken, right? So hysteresis loss directly proportional to B max to the power of x into f, because they would have given voltage variation also, frequency variation also, no? Okay, now let us think of eddy current loss. Eddy current loss directly proportional to volume of iron, eddy current loss directly proportional to thickness square, and eddy current loss as an operating engineer. These are design. Okay, eddy current loss directly proportional to B max square f square. Okay, means the moment question is involved with design, B max square f square only should be taken, not voltage square, because EMF per turn should be taken, some kind of stuff. This is enough. Okay, now see here, volume of iron is increased. Volume of iron is increased by 2 root 2 times. So hysteresis losses should be increased by 2 root 2 times. This will come. We will come to know. Volume of iron is increased by 2 root 2 times. Eddy current losses should be increased by 2 root 2 times. And they did not give thickness variation. So thickness variation will not come. Okay. Now let us think of flux density. Okay. So V equal to, as a design engineer, root 2 pi f B max ACN. Okay. Now come back here. 1 kV primary winding voltage voltage 1 kV is increased to 2 kV. Okay, so this is increased by 2 times. Root 2 pi is anyway constant, and frequency 50 Hz. So frequency is constant. Area of cross section of the core, each side is increased by root 2 times. So area of cross section will be increased by 2 times. And number of turns, same number of turns. Okay, voltage is increased by 2 times, area of cross section is increased by 2 times. So Bmax should be constant in this question. Bmax equal to constant. Now Bmax is constant, frequency constant. So from operation point of view, you don't get any variation here. And Bmax is constant, frequency is constant, and eddy current loss, no variation will come as operating engineer for the given voltage, frequency and all. So altogether, volume of iron is increased by root 2 times. As from design point of view and from operation point of view, you don't get any variation. So hysteresis loss will be increased by 2 root 2 times. Okay, here also eddy current loss will not vary from operation, means double the voltage, something like that they have given. So eddy current losses should be increased by 2 root 2 times. So total losses should be increased by 2 root 2 times. Already you know the answer. 2 root 2 into 55 will be the answer. Now see this question. The iron loss in a transformer. The iron loss in a transformer 312 watt, which 86 watt is due to eddy current. If similar transformer constructed in white, yes, this is design problem again. Right? The iron loss in a transformer is 312 watt, of which 86 watt is due to eddy currents. If similar transformer were constructed in which laminations are of twice the thickness were used, what would be the iron loss for the same impressed voltage frequency? I am unable to understand my own writing. Okay, so it's fine. Now point here is, yeah, means out of 312 watt, total core loss is 312 watt, and out of which eddy current losses are 86 watt, meaning that hysteresis losses will be 312 minus 86, 226 watt. Okay, now for this design problem, okay, if you think of hysteresis losses, okay, hysteresis losses as operating engineer, directly proportional to Bmax to the power of x into f as operating engineer. Now how much is Bmax here? Bmax here means transformer constructed with the laminations twice the thickness of laminations. And one more thing is, many people may feel that when thickness of laminations are increased, area of cross section will be increased. It is not like that. When thickness of laminations are increased, number of laminations will be reduced. Okay, most of the guys will have that particular problem. If this is area of cross section of the core, okay, if I use 2 laminations only, thickness of laminations will be like this. If I use 4 laminations, okay, so if I if I reduce thickness of lamination, number of laminations will be more, but volume of core will be same. Okay, now because in this particular session they said that thickness of laminations are doubled, okay, but volume of core they did not say anything. So volume of core will be same. The moment thickness of laminations are doubled, means number of laminations will be half, such that volume or area of cross section will be same. Now coming to the point here, same voltage, same frequency, everything is going to be same. So Bmax is going to be same. Okay, now if you think of the design engineer point of view, hysteresis loss directly proportional to volume of iron. Are they changing volume of iron? No. So hysteresis losses will not change. So hysteresis losses are going to be 226 only in the second case also. Okay, now let us think of eddy current loss. Okay, so eddy current loss directly, this is design, no, voltage square should not be used, means Bmax square f square. Now voltage is same, frequency is same, area of cross section of the core is same, everything is going to be same, because similar, no, everything is similar. 2 transformers are similar in this case. Now let us think of design. Eddy current loss directly proportional to volume of iron. Volume of iron is going to be same, eddy current losses are going to be same. And again, eddy current loss is directly proportional to thickness square. Thickness of laminations double. So see here, if thickness of laminations is doubled, eddy current should be increased by 4 times. Problem solved. Okay, so net core loss dash. Net core loss is going to be 226 plus 4 into 86 will be the answer. 570 watts. Then now let us consider one more question. See, with 425 25 impressed roll L winding operating engineer. Okay, so this is operating engineer question. What do you say? Because means same transformer voltage and frequency they are changing, that's it. Okay, see, this is watts, this is right. Okay, this operating engineer question, 425 volts at 25 Hz is impressed and LV winding of a transformer, 2500 watts is supplied at no load, meaning that core loss. If the frequency of this impressed voltage is increased to 40 Hz without changing its magnitude of voltage, 20 watt, calculate ratio of hysteresis to eddy currents in 25 Hz condition. Okay, similar problem they asked in GATE, but they have given V by F ratio as constant, but here V by F ratio is not being maintained constant. Okay, good question. Now see here, let us think of total core loss in the first case. Total core loss in the first case is 2500 watt. Total core loss in the second case is 20 watt. In the first case, let me consider this as WH1 plus WE1. In the second case, it is considered that H2 plus E2. Fine. Now, see here, 425 volts, 25 Hz in the first case, and if the frequency of this impressor voltage is increased to 40 without changing magnitude of voltage, it is 20. And here I forgot to write, let us consider x equal to 2. Should be given in the question. Should be given in the question. Okay. Now in this condition, frequency variation is there, but voltage is same. Voltage is same. Okay. Let me consider eddy current loss. Eddy current loss directly proportional to voltage square or directly proportional to B max square F square, because it is operating engineer. If it is design engineer, we are not going to consider here, we have to consider this only. Okay, anything can be considered. Now voltage is constant, so eddy current loss will be constant. So eddy current loss 1 equal to eddy current loss 2. Now let us think of hysteresis loss. Hysteresis loss directly proportional to B max to the power of x. X is given as 2 into F, operating engineer. Okay, so directly proportional to V square by F. Voltage is constant. Voltage is constant. Okay, so frequency is increased, hysteresis losses is to be reduced. Frequency is increased, hysteresis losses is to be reduced. So WH2 should be reduced, meaning that WH1 into reduced in the sense, first case 25 by 40 is going to be reduction. No? Okay, meaning that 25 by 40. 0.625 WH1. Second case. Now let us write these two equations. See, WH1 plus WE1 should be 2500 and 0.625 WH1 plus same as WE1 equal to second case 20. So if I negate this, cancel. Okay, how much is WH? 1 minus 0.625. 2500 minus 2020 by 1280. So hysteresis loss one case is 1280 watt, and obviously eddy current loss one case is going to be 2500 minus answer 1220. Then this particular ratio, okay, because first case is related to 25 Hz only, so 1280 by 1220 is going to be 1.05, we can say, whatever the ratio they asked. Got my point, right? Now if you are unable to solve with me, just first of all open the calculator, open the book, then you please try to solve, because it's recorded only, no? Again you can start. Now let us take this question. Is it operating engineer or design? When 110 volts at 30 Hz is impressed on a transformer, the iron loss is 276 watt, of which 204 watts is hysteresis. If the impressed voltage and frequency are both double, what will be the iron loss? Meaning that it is again operating engineer question only. Okay, so this is operating engineer because same transformer, no? So at 110 volts, 30 Hz, core loss is 276. 204 is hysteresis. Hysteresis will be more normally. Due to hysteresis, if the impressed voltage and frequency are doubled, it's going to be simple question. And in the first case, core loss is going to be 276, meaning that hysteresis loss is 204 they have given. Eddy current loss are going to be 70, 62. Okay, just a minute. Better to type. 72, fine. 72 watts. This is the first case. Now for the same transformer, they double the voltage and they would double the frequency also. So what is Bmax now? V by F ratio. Operating engineer only, no? This is double, this is double, this is going to be constant. Now if you think of hysteresis loss, directly proportional Bmax to the power of X into F, Bmax is constant, forget about it. Directly proportional F. So hysteresis losses in the new case, frequency is double, no? So it should be 2 into 204, directly proportional frequency. Now let us think of eddy current loss. Eddy current loss directly proportional voltage square, or you can say Bmax square F square, anything is fine because it is operating engineer only. If it is design engineer, you are supposed to use this only. Okay. Now voltage is double. Voltage is double. So eddy current losses will be 4 times. Okay. So eddy current loss dash equal to 4 into 72. Now total core loss mu is going to be 4 into 72 plus 2 into 204 will be the answer. Okay, now let us think of, yes, this is the last question. When 110 volts at 60 Hz is impressed on a transformer, the iron loss is 248 watts, of which 25% is due to eddy current. Remaining 75% should be hysteresis. What will be the iron loss when 220 volts 60 Hz is supplied? What will be the iron loss when 110 volts 30 Hz is supplied? X equal to 2. Meaning that operation or design operation. Okay, now operation blue, right? Now see here, when 110 volts 60 Hz, so at 110 volts 60 Hz, the core loss are going to be 248, out of which eddy current losses 25% of 248, 0.25 into 248, 0.25 into 248, 62 watts, and hysteresis is going to be 186 watts. Okay, now let us think of the first case. In the first case, what will be the iron loss when 220 volts 60 Hz is supplied? So 110 volts voltage, 60 Hz frequency, I got this. Now voltage is doubled, frequency is same. Okay, now let us think of hysteresis eddy current. Hysteresis loss is directly proportional Bmax to the power of X into F. Okay, and then they said that X is 2, still means constant as 2, so directly proportional Bmax square F, directly proportional V square by F. Okay, now see here, voltage is doubled, frequency is same. Okay, the moment you take 2 still means constant, variations will become similar. Okay, now hysteresis losses means voltage is doubled, meaning that net hysteresis losses should be 4 times previous hysteresis loss. Okay, because directly proportional voltage square, voltage is double. Okay, here it is 110, here it is 220. So in this case, hysteresis loss dash equal to 4 into 186. Now let us think of eddy current loss. Okay, if you think of eddy current loss directly proportional voltage square, operating engineer, means voltage is doubled, so eddy current loss also should be increased by 4 times. So eddy current loss is dash equal to 4 times 62. Fine. Okay, now let us think of second case. What will be the iron loss when 110 volts 30 Hz is given? Okay, so 110 volts 30 Hz is given. Okay, meaning that see here, at 110 volts 60 Hz we got losses, same 110 volts, but frequency is reduced to half. Okay, let us think of hysteresis loss directly proportional to B max to the power of x. X is nothing but 2 into F, directly proportional to voltage square by F. B max is directly proportional to V by F. So hysteresis losses, voltage is same, so inversely proportional to frequency. If frequency is reduced to half, my hysteresis losses should be increased by 1 by half, meaning that 2. Okay, so new hysteresis losses equal to 2 into volt 186. Okay, now let us think of new eddy current losses directly proportional to voltage square. Eddy current directly proportional to voltage square. Operating engineer, voltage is maintained same, so eddy current losses new, let me use double dot, is going to be same as 62 watt. Okay, means for some people it can be condensed, means if you watch again automatically you will come to know. Okay, very all the best.